Over LeetCode 1971, find if path exists in a given graph. So this is a bidirectional graph with n vertices where each vertex is labeled from 0 to n-1 inclusive. The edges in the graph are represented as a 2D integer array called edges, where each edge subarray denotes a bidirectional edge between vertex u and vertex v. Every vertex pair is connected by at most one edge, and no vertex has an edge to itself. We can determine if there is a valid path that exists from the vertex source and to vertex destination. And we are given edges and the integers n, source, and destination, and we're going to return true if there's a valid path from source to destination, or false otherwise. Now, to do this, I use the breadth first search BFS algorithm, and to do that, I had to first create an adjacency list of the given vertices and their neighbors to represent the graph using a hash map. Now, to construct the graph, I had to iterate over the provided 2D array of edges, and I looked at each subarray, which represented a vertex pair, and I assigned u to the first vertex and v to the destination vertex. And then I added each edge between u and v to the adjacency list graph, where if u wasn't already in the graph, we're going to add it to the graph, and its value is going to be an empty array list. However, we added v to the array list because v is a neighbor to u, and then we did the same for v, where we created a new empty array list but added u to the array list because u is neighboring to v. Since this is a undirected graph, that means at each given vertex pair, they are both neighbors to each other. Now, after this graph has been created by fully iterating through the edges, we created a queue of integers to track which vertices still need to be visited, and a hash set of integers called visited that track what we've already visited. Now, since in this problem we are starting at the source vertex, we're going to enqueue it, and we're also going to add it to the visited hash set, the source vertex, to ensure it doesn't get enqueued again if the source has multiple neighbors. So while the queue is not empty, which means that the vertices, there's still vertexes left to explore, we are going to take the next vertex in line, and if that vertex is equivalent to the destination vertex, that means there's a path that exists, thus we can return true. And otherwise, we're going to conduct BFS, where we're going to grab the list of neighbors from our adjacency list of the given vertex we're at. We're going to grab its neighbors, and then we're going to iterate through each neighbors with a for each loop. And if that given neighbor has not been visited yet, we're going to add that neighbor to visited hash set, and then we're also going to enqueue that neighbor. The reason why we add that neighbor to visited before actually visiting it is to make sure that it does not get enqueued multiple times, just in case that given neighbor is also the neighbor of other multiple vertices. And if we reach a vertex that is equivalent to the destination, we'll return true. And if we never have a vertex that is equivalent to the destination, we're going to return false because there's no path between the source and the destination. And the runtime complexity of this is big O of v plus e, v the number of vertices, and e the number of edges, because in this algorithm, we're going to visit each vertex once and each edge once. And the part I'm most proud of implementing is remembering to add v as a neighbor to u and u as a neighbor to v, because since it's an undirected graph, a vertex pair, it's a two-way street, thus they're both neighbors to each other.